welcome everyone to this notebook on data evaluation of our DataLitMT project. This video basically serves as a walkthrough for this notebook, and we hope that it might help those of you who are not yet familiar with Colab notebooks or with coding for natural language processing in general. However, if you are already familiar with those, we hope to provide you with some additional info and guidance so that you can follow the steps of the notebook more easily, or even adapt some of the code cells to carry out your own analyses. However, please keep in mind that you do not have to change anything in order for the notebook to work. Alongside this advanced level learning nugget, we also have a basic one covering the same topic. But there we use some more basic tools which help you to perform the analysis, namely Excel, for example, or the corpus analysis software nconc. So if you're interested in that, you can check it out. Anyway, this notebook is one of our learning nuggets for data evaluation, and it will mostly provide you with possibilities to learn more about data analysis, data visualization, and data interpretation in the machine translation context. And hopefully it will enable you to use the acquired knowledge and skills to carry out meaningful data analyses of your own in the future. In this notebook specifically, we will analyze how integrating machine translation into the translation process can affect the target text we produce. So we will analyze text data, or more specifically target text data, in different translation scenarios from English into German. Namely, we want to look at one raw or unedited NMT output. NMT stands for Neural Machine Translation, and this output has been produced by DeepL from an English source text. The second type of target text we want to look at are post-edited versions of this NMT output, or MTPE for short, and these have been produced by post-editors. And thirdly, we look at human translations from scratch, which have been produced from the source text by professional translators. As always, the notebook starts by introducing relevant concepts and helpful background information on the topic of the notebook. So, for example, in this notebook, we start by talking about neural machine translation systems and the possibility of deceptively fluent NMT output. Then we go on by explaining the concepts Translationese, Machine Translationese, and Post-Editese, and also the concept priming. If you are already familiar with those, you might want to skip the introduction. However, if you are not, then we recommend that you give it a quick read. Also, we included interesting references for the introduced topics and concepts, though you might want to check that out if you're interested to learn more about them. After this theory part, we go on by introducing a hypothesis, which will guide us during our data evaluation. More on that one later. And then, finally, at section 0, you have reached the beginning of our practical part. And this practical part of our notebook is a mixture of both text and code cells. Again, don't worry too much about the code cells, as I will explain everything as we go along. And also, each code cell is always accompanied by a text cell explaining what the code below does. Now, in this notebook, we will start from the following hypothesis. We are expecting lexical density and variety to be lowest in unedited NMT output, higher in post-edited NMT output, and highest in human translation. Both of these concepts, so lexical density and variety, will be explained in their respective sections in more detail. You can navigate to these sections just by scrolling down or by opening the table of contents, which you can find in the upper left corner by clicking on this icon and then clicking on the respective section. For example, we discuss lexical variety in section 2 and lexical density in section 3. But for now, let's return to section 0 to start with the demonstration of the notebook. And section 0 actually only serves the purpose of ensuring that you meet the requirements to successfully run the notebook in your environment. And the first thing we need to do for that is that we need to clone the DataLitMT GitHub repository to access all necessary files, which means we need to access our target text. And we can clone the repository by running the first code cell here below by clicking on this icon. So now we can see that the cell or the code has been run successfully, since we can now see a green check mark left to the cell. Below the cell you can also see a bit of protocol data if you want, but since there's no relevant data for us now, we can just clear this out by clicking on the X. Now we need to navigate to the folder that contains our target text, which you can access with this path. And this cell, when we run it, should also indicate all the files that are contained in the folder. And here in the output of the cell, we can now see that the folder documents contains the source text, the 5 human translations, the 5 post-edited versions of our NMT output, and of course the NMT output itself. If you would like to, you can also confirm that these files are in the folder, and you can see that when in the sidebar you click on Files and open the DataLitMT folder, and then you basically just follow the path which is indicated here in the code cell. So we open Learning Resources and Machine Translationese and Post-Editese and Documents, and we can see that all of the files are here. So in the next step we need to install 2 little helpers, if you want, 2 libraries. The first one is docx2txt. We need that because the files in our folder are actually Word documents, and to access the text in the files we need to extract it, and this is where this library comes in. If you want to learn more about it, you can visit the repository here. The second one is the module Lexical Richness, which will help us calculate the lexical variety we talked about earlier. So this code cell just installs those 2 libraries. And again, the cell produces a lot of output, which you can later just clear out if we have confirmed that both libraries have been installed correctly, which is now the case. And that's it, you're ready to go. So in section 1 of our notebook, we are going to extract the text from our files for processing. And we save this text into variables, little containers if you want, to make them accessible for later processing steps. So what we're going to do is we will create the variable text_nt for the text of the NMT output, the variables text A1 to A5 for the post-edited outputs, and the text B6 to text B10 variables will contain the text from the human translations from scratch. And to do that, we just import docx2txt and then extract all the text from the files in their respective variable. And what we will also do is we group all these texts together in a list to facilitate later processing. We now completed sections 0 and 1 of this notebook, and I wanted to add that these are also the first ones you would need to adapt if you wanted to customize this data evaluation. For example, if you wanted to analyze your own target texts. You would then need to start here, in fact, because instead of cloning our repository, you could, for example, mount this to a drive and import the text you want to analyze. Then you, of course, would need to change the file names here in red and perhaps the variables, for example. However, keep in mind that we use these variables quite often in our course cells, so it would be much more work if you changed these variables. For example, if you just wanted to use other text but also would like to use 5 post-edited outputs and 5 human translation and compare it to 1 NMT output, you could simply just change the file names and just leave the variables as is, and that would be easily possible. However, in this video we will continue to work with our target texts, and in section 2 we want to analyze how lexically diverse their vocabularies are. And this is called lexical variety, but it's also referred to as lexical diversity or lexical richness, for example. Keep in mind that we expect lexical variety to be lowest in raw or unedited NMT output, higher in post-edited NMT output, and highest in human translation. A measure for lexical variety is the type token ratio in a text. Tokens are all the words in a text. Types, however, are only the different word forms in a text. So words or word forms that occur more than once in a text are only counted once. Now, to get the type token ratio, we divide the number of types by the number of tokens. And the higher the type token ratio, or TTR for short, is, the higher the lexical variety in a text. Now, for illustration purposes, we can calculate the type token ratio for one of our target texts. For example, the first post-edited NMT output, the text of which is stored in the variable text underscore A1. For that, we just import the module lexical richness, and now we want the module to give us the number of tokens, the number of types, and we want it to calculate the type token ratio. So we run the cell, and now we can see that text A1 has 301 tokens, 159 types, and a type token ratio of 0.528, etc. And that is all very nice to know, but it doesn't really tell us enough yet to confirm or disprove our hypothesis. So to get meaningful data, we need to calculate the type token ratio of all our target texts. And we can do that by running this code cell below. In this code cell, we will use the target text list that we created earlier at the end of section 1. We also create 3 new lists for tokens, for types, and for the type token ratio values. So basically, this code cell will calculate the tokens, the types, and the type token ratio for each text, and will then add the results to the respective list. So basically, we again group our results in variables, or lists in this context, to later access them for further calculations and for visualization, in fact. So we can run the cell. And if you're not familiar with lists in Python, you need to know that the count starts at 0. So basically, 0 represents the first element in our target text list, which is the NMT output, which has not been edited in any way. Consequently, 1, or the second element in the list, represents the text A1, so the first post-edited output we just analyzed individually. And again, this count follows the target text list from section 1. Now, here we can see that the NMT output has 208 287 tokens and 143 types, which is interesting because depending on which tools you use for your data analysis, your results in this step might slightly differ due to differences in tokenization. And basically what that means is you will get different or varying results if you use different tools. For example, in our basic level learning nugget, we used nconc to count the types and tokens of our target text. And nconc told us that the NMT output had 287 tokens, which is the same value we get here, but it told us that it had 2 types fewer, so only 141, which ever so slightly decreases the lexical variety in the result. It is just something that you can keep in mind. So now our first data analysis is complete, but we ended up with numbers and values in lists, which is great, true, but it's not really easy to interpret, is it? So we recommend that you visualize this data in tables or charts, which is what we'll do in section 2.2. For this we will use the library matplotlib, which is arguably the most common library for visualizing data in Python. It's very versatile and you can learn more about it here via a link, which will lead you to the webpage of matplotlib containing a user guide and some more explanations. So we just import matplotlib. We don't need to install it since it already comes with Python. And then we have a look at this rather big code cell. Don't be intimidated, it is really easier than it looks. So for these big code cells, we often included comments just to provide you with some additional information. So in this case, this comment tells you that the code cell here will create a table to visualize the analysis results. But before actually creating the table, we need to prepare some lists to fill the table actually. Obviously, we want our target text names to be included, which we achieve by saving them as strings in a target text titles list. Then we need to indicate the data we want to fill our table with. And this we can do with the list data. And this list actually is a list of lists because we need to include various elements from different lists into this. And you see that each line here will represent one line in the table, and each column separated by commas will be one column in the table. And since you now know that Python lists start their count at 0, you can understand that the first line of this data list is concerned with the NMT output, the first element in all of our lists. So you see that its title is included, then the number of its types, the number of its tokens, and its value for the GTR. And we round this up to 3 decimal points just to make it more visually appealing. Then we define the labels for our columns of the table, which we want to print in bold just to make it more visually appealing. And we achieve that by including the names of the columns and with these characters around them. And then we want to color the cells, which of course is optional, but you make it clearer this way. So for example, we could color the cells for the NMT output red, the ones for the post-edited outputs in yellow, and the human translation cells will be green. And then down here, this line finally creates the table. So we just define for all of the different parameters, cell text, co-labels, colors, and cell colors, that the contents of our list shall be used for creating the table. Then we run the cell, and then you can see that the table has been created. And this is already a much clearer representation of our data compared to our initial representation, which just were lists and values. However, before interpreting the results of our analysis, we will create a graphical representation of the data. Now, of course, there are different ways of representing data graphically, and they are different charts, of course, and Matplotlib supports most of them. But in this notebook, we opted for the creation of line charts. And the first one we want to create will plot us types against tokens. So we give it a title, and on the x-axis we want our text, on the y-axis the number of types and tokens, and on the x-axis we want, for example, short target text titles like NMT A1 to A5 are the post-edited output versions, and B6 to B10, of course, the human translations. And these short titles shall be applied to the x-axis, and then we want to create two lines. The first one will represent the number of types, and we get the values from our types lists. And the second line will represent the number of tokens, and the values come from the tokens list. The blue line will represent the types, and the orange line will represent the tokens. And we can add a legend to this chart for clarity that indicates just that. Please note that we delimit the scope of the produced chart because we start from 100, not from 0, just for clarity and to make it more visually appealing. And for clarity, we also add dotted lines between the different sections of this chart. And this is what this line right here will achieve, because it will divide the chart into 3 sections, one for the MT output, one for all of the post-edited versions of its output, and one for the human translations. So we can run the cell and create the line chart. Now, and what does this chart actually show? Well, for example, we can see that B10, a human translation, has the highest number of both types and tokens. B7, another human translation, on the other hand, has the lowest number of tokens and also a very low number of types. Now, that's all very nice, but this chart doesn't tell us a lot about lexical variety yet. Instead, we need to visualize the type-token ratio for each text. So we can look at the cell below that will achieve just that. So again, we add respective titles to both the chart and the axes. And then instead of 2 lines for the numbers of types and tokens, we now access our type-token ratio list and the elements in this list to plot the type-token ratios of our different target texts. We again delimit the scope of this chart and again add our dotted lines with the code in this line here. Now we can run that too. And here we can see that 2 of our post-edited texts, A1 and A2, have higher type-token ratios than the NMT output. The other post-edited outputs, A3 to A5, show relatively similar values compared to the NMT output, as does the human translation B9, which is slightly surprising and different from the results obtained in our basic level calculations, which you can access here via the link, which will lead you to the paper of the basic level. And then the human translations B6, B7 and B8 have higher type-token ratios than the NMT output and all of our post-edited texts. B10 also has a relatively high type-token ratio and is only just beaten by the post-edited text A2. Now, what do these results actually mean for the hypothesis that we introduced at the beginning of our notebook? Well, I won't go into too much detail here, since you can read the section 2.3 and consult the references, but maybe briefly we can say that lexical variety is relatively low in the NMT output, probably because NNT systems tend to prefer the translation solutions most frequently used in their training data and to ignore less frequent words. Post-editors then may or may not, as we've seen in the chart above, add lexical variety to some degree. On average, the human translations have a higher lexical variety than the NMT output and the post-edited text. Then, of course, our results also show some exceptions to these tendencies. For example, the outliers of A3 to A5 and B9. Previous studies have shown clearer results. For example, Terrell 2019 found out that lexical variety was lowest in NMT, higher in post-edited texts, and highest in human translation. Please keep in mind though that we only used 11 one-page documents for our analysis. Terrell used a much larger sample size. Now, moving on to lexical density. Lexical density describes the amount of information in a text, and this can be assessed by calculating the ratio between the number of content words and the overall number of tokens in a text. Luckily, we already know the numbers of tokens for our target texts, which is why we can just use the variables from section 2 again in this section. Unfortunately, we don't really know how many content words our target texts have, and it is not that clear-cut what exactly content words are. In general, content words carry semantic content and contribute to the meaning of the sentence in which they occur. For example, Terrell 2019 counts nouns, verbs, adjectives, and adverbs as content words. However, we ask ourselves if by nouns he also means proper nouns, and by verbs he also includes auxiliary verbs. And this actually presents us with a problem that is similar to the problem that we encountered in section 2, where we showed you about the different methods of tokenization, which can result in different values for lexical variety. And depending on what you count as content words, the values for lexical density can also widely differ. Which is why when calculating automatic measures such as lexical variety or density, we want to be as transparent as possible about our methods. And in our analysis, we're counting as content words nouns, proper nouns, verbs, but no auxiliary verbs, adverbs, and adjectives. To automatically find out how many content words there are in our target texts, we need to carry out some preparation steps first. And to this end, we will use spaCy. spaCy is a free open source library for advanced natural language processing in Python. And if you want to learn more about this tool, you can check out the 101 page, which we linked here. First, spaCy needs to know that we work with German text data, so we not only need to import spaCy itself, but also a German language model, or a so-called trade pipeline. And we will use this pipeline to take out text with part-of-speech information, which basically means that we ask spaCy to attach a POS tag to every word in our text, for example, website noun. To use this feature, we save the pipeline in a variable NLP first. Now this cell also imports spaCy, downloads the module, and then loads it into the variable for further processing. Now that's done, we can clear the output and can define the text we want to tag, which we do by using the NLP function and saving the text which then has been tagged in variables. As we did in section 1, we will also then group all of the tagged text in order to enable further processing down the line. Now, that was really quick, wasn't it? Unfortunately, we do not see very much of this process, so we would like to present it in a little more detail in section 2.3. Now, in this section, we would like to show you firstly how these tagged tags look like. For example, we will specifically look at the post-edited output A1. And if we now run this code cell, we see that the code prints the tokens vertically and assigns a POS tag to each of them to the right. If you want to learn more about the POS tags in spaCy and how to interpret them, you can find more information in this article right here. For example, you can see that bereitgestellt has been tagged as a verb, the comma has been tagged as a punctuation mark, and so on, and website as a noun, etc. Now, the more interesting part is that we now can count the POS tags, or the content words if you want. And as outlined earlier, we are only considering the following parts of speech, or tags: noun, prop n for proper noun, verb, adjectives are assigned adj, and adv adverbs. The numbers of different tags will then be added together to obtain the content word count for said text. And this cell will achieve exactly that. So we first create a new list, and then for every token in the text, for example Zuverlässigkeit, we append the POS tag to this new list. So in this case, noun would be appended to the list or content words. Now once this step is completed, we just need to specify the desired POS tags again, count them, and add their numbers together. And to do this, we just run the cell, and the output of the cell tells us that text A1 has a content word count of 146. Now, as you may have already noticed, not all the assigned POS tags are necessarily correct. You can see this very prominently at the enumerations. For example, 3.2.2 has been assigned the POS tag verb, and 3.2.9 has been assigned the POS adverb. This causes a problem for us, because we count adverbs or verbs, for example, as content words, but not numbers or numerals, for example. Unfortunately, this error can be seen throughout the text, and in total 7 POS tags are incorrectly assigned. Now, for this analysis, we would like to calculate an error rate if you want for this text, and we want to project this error rate onto the content word counts for all other texts, because we expect this to happen in other texts as well. And this cell right here will do exactly that. As I said, in text A1 there are 7 incorrect POS tags. In total we have 146 content word POS tags. So we just multiply by 100 to get a percentage, and then we are left with an error rate of approximately 4.8%. We will use this error rate, as I said, to project it onto all other texts in order to account for all incorrect POS tags. Once we've understood this, we can count the content words for each text, and the following cell essentially repeats what we just did for the text A1, but this time for all target texts individually. And this newly created list content words will then contain the number of content words for each text. We can run the cell, and this output now tells us that, for example, the NMT output has 133 content words. Now for further processing, we need to extract the numbers of content words from the list content words. So we can do that, for example, for the NMT output by specifying the index 0, as the NMT output, as always, is the first element in the list. And we can save the number in a variable which we can call content words NMT, for example. Run the cell. And then in section 3.4 we can continue to actually calculate the lexical density. And we can do that by dividing the number of content words by the number of tokens. And again, we take the number of tokens from our tokens list from earlier. And then we can save the results in variables, and these variables again in lists, to make it easier to visualize our lexical density values later. So we just want the cell, and then we can see that our list, lexical densities, now contains the lexical density values for all our target texts. And then, as outlined in section 3.2, each content word count will have an error of 4.79% to account for incorrectly assigned POS tags. To calculate this, we divide the individual lexical density values of the text by 100 and multiply this with the POS error. And you probably guessed it, we then save these results in variables again and group all of these variables in a list that we call density errors to facilitate later visualization of these error rates. And in the output of the cell we can see that this list now contains all the density errors for our texts. Now, after all of these steps of calculating the lexical density, we are finally ready to visualize the results of our data analysis. And we'll start by creating a table. And I won't go into too much detail regarding the code to create the table here, since the structure is basically the same as the one we used in section 2.2 to create the table for the lexical variety values and the type token ratios. So basically we just add more columns, and we have our target text titles on the left, then the content words, then our tokens, and then the values for lexical density that are round to 3 decimal points, and of course the density errors, which are also round to 3 decimal points. So we can create the table, and of course this table now pretty clearly summarizes the results of our data analysis. However, this time it might make even more sense to use a line chart for visualizing our data, since we now have to include the density errors, and these are a little bit hard to interpret only by looking at the numbers. So we will again create one of these line charts. And again, the code cell we use is pretty similar to the one we used in section 2.2 to plot the lexical variety values of the different target texts. But of course this time we will use our lexical density values in the list lexical densities, and we of course will create the error bars, which are created with these two code lines here. And for creating these we will of course use our density error values, and we will color them in red and black to set them apart from the rest of the chart. And we will also again add our dotted lines to split this chart into 3 sections. The first one regarding the unedited NMT output, the second one regarding the post-edited versions of this output, and the third one regarding the human translations. So we can click on create, and now this chart clearly shows us that the NMT output has the lowest value for lexical density. The chart also shows that all post-edited texts, so A1 to A5, have a higher lexical density than the NMT output. However, A3 to A5 show relatively similar values compared to the NMT output. The human translation B7 has the highest lexical density. B6, B8 and B9 also score relatively high. B10 is just beaten by the post-edited text A2, but it still has a higher lexical density than the other post-edited texts and the NMT output. Overall, the picture for lexical density is a bit more clear-cut than the picture for lexical variety. Now, in the introduction, we hypothesized that given what we know about machine translationese and post-editese, lexical density should be lowest in raw NMT output, higher in post-edited output, and highest in human translation. Despite the exception of the human translation B10, here in the chart on the right, and relatively high errors we needed to account for, Our analysis results generally seem to confirm this. Please mind, however, that our sample size was relatively small as we only used 11 one-page documents. It is interesting to note, however, that other researchers, such as Terrell 2019, are unsure whether the degree of lexical density really represents a systematic difference between the different translation scenarios or not. So, we've almost reached the end of this notebook. And before you go, I wanted to briefly point your attention towards the conclusion, as it tells you a lot about the interesting concepts that we got introduced to along the way. It also sums everything up that we've learned today. In general, we can say that we could confirm our introductory hypothesis. Both lexical variety and density seem to be lowest in NMT output, higher in post-edited output, and highest in human translation, with the picture for lexical density being a bit more clear-cut than for lexical variety. At the end, we also included a small paragraph on what that means for us as professional translators and post-editors. So we invite you to work through this notebook yourself and learn more about the interesting concepts of machine translationese and post-editese in translation data. But now, that's it. Thank you very much for your attention. We hope you enjoyed it and we hope you learned something. If you are interested in other learning resources, you can visit the DataLitMT website. Goodbye.